This video is going to look at 1,2 and 1,4 additions. The other main reaction in this chapter involves adding our hydrogen halides to our conjugated dienes, giving us two possibilities. We have a 1,2 addition where we're adding our H and our halogen to adjacent carbons. For 1,4 addition, we're adding two carbons that have a 1 and 4 relationship. So notice here I've labeled my carbons 1, 2, 3, and 4 of my conjugated system, right? These would not be the numbers that we use to name this compound. We're using this just to associate where my groups are going. So if we were to add HBr to this, we'd end up having 1,2 addition as our major product. And you can see here the reason why is we're at low temperatures. So the H and the Br are located at positions that are 1, 2, right next to each other. This means that my double bond on positions 3 and 4 hasn't reacted. We didn't call it this in 3570, but this is effectively what you did. We added an H and a Br to next door carbons. Here we're going to add more complexity because we're a conjugated system. If we add this 1,4, notice what happens here. My double bond has again shifted. So here my hydrogen has been added to carbon 1 and my bromine has been added to 4. That makes it a 1,4 addition. Let's talk about why this is. Let's go through the mechanism that explains how these two products are formed. If you'd like to try this on your own, you can go ahead, draw in arrows, and provide structures in each box. Pause the video now. The first arrow is already drawn for you, and here we have a symmetrical molecule, so it doesn't matter which double bond we start with, but if we go out and grab the hydrogen, we have to push the electrons onto bromine. As a result here, I can see that I have a double-sided arrow, so I have a resonance structure I need to draw. Resonance here would move the double bond over to alleviate the positive charge on carbon 2. This would place the positive charge on carbon 4 with the double bond moving from 4 and 3 to 3 and 2. At this point, my Br minus can go ahead and add to position 2 or to position 4. Notice here, when the bromine adds to position 2, that is very similar to what we used for this mechanism in 3570. My bromine and hydrogen are right next door to each other. The key difference here is that when the double bond is used for resonance, we end up having a relationship between the hydrogen and bromine that are added from carbons 1 and 4. Here, seeing the H and the Br next to each other, that tells us this is our 1,2 addition product. Here, having the hydrogen and bromine 4 spots away gives us our 1,4 addition. Let's talk a little bit more about why this occurs. So if we were to add the hydrogen to the 2 position, we would still create a secondary carbocation that the bromine can come and add to. As a result, we would still see 1,2 addition. However, this carbocation isn't formed because it is not resonance stabilized. So if we were to get rid of our hydrogens and our bromines, we would see here there's no way to get conjugation from the double bond. So this is not a resonance stabilized carbocation. This is just a standard secondary carbocation. In the mechanism we just went over, this gave us the ability to have resonance, thereby splitting the positive charge onto 2 positions. So we have now a new type of carbocation known as an allylic carbocation that's much more stable because it's not just one carbon holding all the positive charge. We're going to need to slightly change the way we rank our carbocations. We used to only have primary, secondary, and tertiary. Having an allylic position basically bumps it up 1 level, meaning a primary allylic is equal to a secondary carbocation, and a secondary allylic is equal to a tertiary alkyl or a tertiary carbocation. So while it would look like we'd be generating a secondary at either spot here, a secondary allylic is better than a secondary, and that's why the mechanism works. This reaction also introduces the concept of kinetic and thermodynamic control. When we're at lower temperatures, even though it's less stable, we're going to be able to produce more of the 1,2 product. If you want to add heat or a catalyst, you can end up shifting to force equilibrium to generate our major product to be our thermodynamic, meaning our more stable. So we would have a little bit faster reaction, creating our kinetic product, which would just be our 1,2. Here would have my chlorine add to that position. And if I were to have 1,4, create the more stable product, I would end up with having the resonance. You can kind of see here when we think about more stable, the more substituted double bond is going to be our more stable product. Let's continue with that example. Here I'm asking you to draw the carbocation intermediates that are both possible, as well as the new final products. Pause the video now. We are symmetrical, so it doesn't matter which double bond you have here, but for the kinetic product, we're going to create our carbocation at the allylic position. From here, we can have our nucleophile come right in to create our kinetic product. Here, we would see this as 1,2 addition. For a thermodynamic product, we would go and use resonance to shift the carbocation from the secondary position allylic to the primary allylic position. Now, my chlorine can come in, add to my carbocation to create my thermodynamic product. That wraps up this video.